Nenomatica, where mathematics meets YouTube excellence. In this lesson, we analyze systems built from even powers, absolute values, and even roots. We'll see why each term must be zero, and how the solution set is the intersection of the zero sets. First, here is the example system we will study. Step 1. Understand the non-negativity facts. Even powers, absolute values, and even roots are always greater than or equal to 0. Step 2. Analyze the first equation. Because each addend is non-negative, the sum equals 0 only if each term equals 0. So f of x equals 0, and g of x equals 0. Step 3. Analyze the absolute value equation. A sum of two absolute values is 0 only when both are 0. Thus f of x equals 0, and g of x equals 0 again. Step 4. Analyze the even root equation. Even roots are non-negative, so their sum is 0 only if both are 0. That again forces f of x equals 0, and g of x equals 0. Step 5. Put the facts together. Define A as the set of x, where f of x equals 0, and B as the set of x, where g of x equals 0. The system solutions are exactly the intersection A cap B. Step 6. A useful generalization. If we have the sum of non-negative terms equal to 0, then each term must be 0. Step 7. The practical strategy. Solve f of x equals 0 and g of x equals 0 separately, and then intersect the solution sets. Quick challenge. Solve, open quote, quantity x squared minus 1 squared plus quantity x minus 1 to the fourth equals 0, close quote. Pause and predict why every term must be 0 and what x must be. Reveal, each term is non-negative and the sum is 0, so each term must be 0. From x squared minus 1 equals 0, we get x equals plus or minus 1. And from x minus 1 equals 0, we get x equals 1. The intersection is x equals 1. Summary. We used non-negativity to force each term to 0. Concluded the solution set is the intersection of the zero sets, showed a generalization with a third term, and practiced with a quick challenge. We will solve a radical and polynomial mix by following the even power, absolute value, and square root zero sum idea. First, let's show the example. Step 1. Analyze the structure. The fourth power, the absolute value, and the square root are each non-negative. Therefore, if their sum is 0, each individual term must be exactly 0. Step 2. Set the inner expressions equal to 0. Even powers, absolute values, and square roots become 0 only when their inner expressions are 0. This yields a system of 3 polynomial equations to solve. Step 3. Solve the quadratic. We factor x squared plus x minus 6 into left parenthesis x plus 3 right parenthesis times left parenthesis x minus 2 right parenthesis. Therefore, x equals negative 3 or x equals 2. Example. We will solve the equation where a sum of 3 non-negative terms equals 0. The equation is, open parenthesis, x squared minus 1, close parenthesis, to the power 74, plus the absolute value of x to the power 75 plus 1, plus the 76th root of x squared plus 3x plus 2 equals 0. Key idea. Each term is non-negative. The first term is a large even power, so it is greater than or equal to 0. The absolute value is always greater than or equal to 0, and any even index root of a non-negative number is also non-negative. Therefore, because a sum of non-negative terms equals 0, every term must individually be 0. So we set each term to 0. First, x squared minus 1 equals 0. Second, the absolute value of x to the 75 plus 1 equals 0, which means the inside must be 0. Third, the 76th root equals 0, which means the radicand equals 0. Now solve each. From x squared minus 1 equals 0, we get x equals plus or minus 1. From x to the 75 plus 1 equals 0. Since the exponent is odd, we get x equals negative 1. From x squared plus 3x plus 2 equals 0. Factor to get x plus 1 times x plus 2 equals 0. So x equals negative 1 or x equals negative 2. The solution to the original equation is the intersection of these 3 sets. From the first, we have braces -1 and +1. From the second, we have just -1. From the third, we have -1 and -2. The common value across all three is -1. Here is a quick number line view. We mark -2, -1, and 1, and highlight the shared solution -1. Verify by substitution. At x equals -1. The first term becomes 0, the absolute value becomes 0, and the 76th root of 0 is 0. So the entire left side equals 0, confirming our answer. Final answer. The solution set is the single value -1. Example. We will solve a radical equation exactly following the given step order and rules. Problem. Solve the equation. The fourth root of x cubed minus 4x squared plus x plus 6 plus the square root of x squared minus 7x minus 8 equals 0. Step 1. Set the equation and isolate radicals. Both radicals are already isolated on the left side. Step 2. Because we have an even root and a square root, each radical is non-negative. The sum equals 0 only when each radical equals 0. Step 3. Set each radicand equal to 0. Step 4. Solve the quadratic equation x squared minus 7x minus 8 equals 0. It factors as x minus 8 times x plus 1 equals 0, so x equals -1 or 8. Step 5. Test each candidate in the cubic equation. 4x equals 8, the value is 270, which is not 0. 4x equals -1, we get 0. So only x equals -1 satisfies both equations. Example. We will solve the radical equation step by step, exactly following the given structure. Radical equation. If the sum of two square roots equals 0, then each square root must be 0, because square roots are non-negative. Step 1. Set the equation and analyze the radicals. We conclude the only way their sum is 0 is when both square roots are each 0. Square root 0 condition. A square root equals 0 if, and only if its radicand equals 0. Step 2. Solve each radicand equal to 0. Quadratic factoring. Factor the quadratic and solve. Step 3. Factor the quadratic equation on the left. This gives roots x equals 3 and x equals -2. We highlight these new values. Rule. Polynomial root testing. Substitute the candidate values into the cubic to check they are roots. Step 4. Test roots in the cubic equation. Evaluate at x equals 3 and at x equals -2. Both evaluate to 0, so both are common roots. Rule. Solution set intersection. The solutions are the common roots of both conditions. Step 5. Write the solution set. The solution set is -2 and 3. Quick challenge. Can you explain why a sum of non-negative numbers can be 0 only when each is? In this example, we will solve a radical equation step by step. Step 1. Understand the domain and structure. Radicals like square roots and fourth roots are always non-negative for real numbers. Therefore, if their sum is 0, each must be 0 individually. Step 2. Apply the zero-sum property for non-negative quantities. If a plus b equals 0, and both are at least 0, then each is 0. This gives a system. The fourth root equals 0, and the square root equals 0. Reducing each radical equals 0 forces the radicands to be 0. Step 3. Solve the quadratic equation, first to get potential solutions. We can factor or use the quadratic formula. Factoring gives x minus 1 times x minus 2 equals 0. So the candidates are x equals 1 and x equals 2. Step 4. Check each candidate in the original radical equation to avoid extraneous roots. Always substitute back. 4x equals 1. The fourth root becomes the fourth root of -8, which is not real, so discard x equals 1. 4x equals 2. Both radicals become 0. And the cubic x cubed plus x minus 10 also equals 0. So x equals 2 is valid. Quick challenge. Why does the sum of two non-negative radicals equal 0 only when both are 0? Pause and think for a second. Step 5. State the solution set clearly. The only real solution is 2. First, display the word example. Then show the problem in bold orange math. Step 1. Recognize that every term on the left is non-negative. A sixth power, an absolute value, and a square root are each greater than or equal to 0. Therefore, the sum can equal 0 only when each term equals 0. Step 2. Reduce each condition to an equivalent equation. A sixth power equals 0 precisely when its base is 0. Absolute value equals 0 when the inside is 0. A square root equals 0 when the radicand is 0. Following the structure shown, we now solve the quadratic x squared minus x equals 0. Factoring gives x times x minus 1 equals 0, so the solutions are x equals 0 and x equals 1. Both candidate values must satisfy all three reduced equations. Check x equals 0, each term becomes 0. Check x equals 1, each term becomes 0 too. Therefore, the common root set is braces 0, 1. In this lesson, we will solve a radical system and find z. We will use the idea that a sum of non-negative terms can only be 0 if each term is 0. Here is the equation. The square root of x cubed minus 3 plus the quantity x to the 9th minus y squared minus 23, all raised to the 10th power, plus the fourth root of y plus c equals 0. Each of these three parts is non-negative. A square root is never negative, an even power is never negative, and a fourth root is never negative. So if their sum is 0, then each term must be 0. We set each radicand and the base of the even power to 0. First equation, x cubed minus 3 equals 0. That gives x cubed equals 3. We will keep x cubed as 3 for substitution. Second equation, x to the 9th minus y squared minus 23 equals 0. Since x cubed is 3, x to the 9th is x cubed cubed, which is 27. Substitute and simplify to solve for y. Third equation, y plus c equals 0. So z equals negative y. Substituting y equals plus or minus 2 gives z equals minus 2 or plus 2. In set form, z equals plus or minus 2. Quick check. For either pair, y equals 2 and z equals negative 2, or y equals negative 2 and z equals 2, and with x cubed equal to 3, each term becomes 0, so the original equation is satisfied. Therefore, the solutions are x cubed equals 3, y equals plus, the solutions are x cubed equals 3, y equals plus or minus 2, and z equals plus or minus 2. The question asked for z, so we report z equals plus or minus 2. Example. We will solve the radical absolute value equation for y. We will follow the exact step structure from the provided solution. First, set each non-negative term to 0, then solve the radical part, substitute into the absolute value part, and finally solve for y. Step 1. Because a principal sixth root and an absolute value are both non-negative, if their sum is 0, then each expression must be 0 individually. Step 2. If a principal root equals 0, then its radicand must be 0. So we set x to the 5th minus 2 equal to 0, and solve for x to the 5th equals 2. Step 3. Since the absolute value of an expression is 0 only when the expression itself is 0, we drop the bars and then substitute x to the 5th equals 2. Notice x to the 10th equals the square of x to the 5th. Step 4. Isolate y. Move the constants to the right to obtain y equals negative 4 minus 5, which equals negative 9. Example. We are given a radical sum equation. Each term is non-negative. An absolute value, a fourth root, and a square root. We will solve it step by step, reproducing the exact algorithm from the prompt, and find x and y. Step 1. Because a sum of non-negative numbers can be 0 only when each addend is 0, we set all three inner expressions to 0. Step 2. We solve the quartic by substituting t equals x squared. This turns the equation into a simple quadratic. Then we apply the quadratic formula. The solutions for t are 4 and negative 1. Hence x squared equals 4 gives x equals plus or minus 2. X squared equals negative 1 has no real solution. Step 3. We must also satisfy the fourth root radicand equal to 0. Check x equals 2 and x equals negative 2. Both evaluate to 0, so they are valid. Step 4. Now solve the third equation for y for each x. Case 1, x equals 2. We get y squared minus 2, y plus 1 equals 0, so y equals 1. Case 2, x equals negative 2. We get y squared minus 2, y minus 1 equals 0, hence y equals 1 plus or minus square root 2. Step 5. Collect the solutions. The order pairs are x equals 2 with y equals 1, and x equals negative 2 with y equals 1 plus square root 2 or 1 minus square root 2. Example: we will solve a product equation with an absolute value and a square root, then filter solutions by the domain of the radical. Step 1. Apply the zero product property. A product is 0 when at least one factor is 0. So we set each factor to 0 separately. Step 2. Solve each equation. We use basic quadratic solving. First, x squared plus 3x minus 4 equals 0 factors to x plus 4 times x minus 1. So x equals negative 4 or x equals 1. Second, the absolute value equals 0 only when the inside is 0. So x squared minus 1 equals 0, giving x equals plus or minus 1. Third, the square root is 0 when the radicand is 0. X squared minus x minus 6 equals 0, which factors to x minus 3 times x plus 2, giving x equals 3 or x equals negative 2. Step 3. Combine all candidate roots. Our pool is negative 4, negative 2, negative 1, 1, and 3. Step 4. Enforce the domain of the square root. The radicand must be greater than or equal to 0. That is, x squared minus x minus 6 is greater than or equal to 0. Factoring gives x minus 3 times x plus 2 greater than or equal to 0. So the allowed x are less than or equal to negative 2 or greater than or equal to 3. Step 5. Filter the candidates by the domain. Negative 4 and negative 2 are allowed. 3 is allowed, but negative 1 and 1 lie between negative 2 and 3 where the radicand is negative, so they are rejected. Final answer. The solutions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.